So let's say if we have a solid, a rectangular solid, what's going to happen if we apply a downward force on a solid? What do you think is going to happen? Let's say if we hang a mass on it. All solids have the ability to stretch beyond their natural length. And the amount in which they stretch depends on the force that's applied. So here we have a mass hanging on it. And the downward force is equal to the weight force of that mass. Now Hooke's law states that the force is proportional to the change in length of the solid. So the change in length will be the difference between these 2 points. It's the difference between the original length of the solid, which is L0, and the new length, or the final length, of the solid. So delta L is L final minus L initial. Perhaps you've seen Hooke's law expressed this way: F is equal to negative kx. So it's very similar. If you increase the applied force, the change in length will increase. Now let's make a graph that describes the force and the change in length. So we're going to put the force on the y-axis and the change in length on the x-axis. So initially, there's going to be a linear relationship between F and delta L. And then after that, the relationship won't be so linear. So it's going to be curved. Let's call this point A, point B, point C, and point D. Now, point B is known as the proportional limit, which I'll explain what that is. You could probably know or guess what it's going to be based on the wording of it. Point C is the elastic limit. And point D is the breaking point. So, in the region between A and B, where it goes up to the proportional limit, that region, notice that it's linear. It follows the equation F is equal to K times delta L. So it follows Hooke's law. Now between points A and C, we have something that's known as the elastic region. Now the elastic region is basically the region where it's elastic. If you remove the external force, the object will return to its natural length. It won't be deformed. It's going to regain its original shape. Now, once you pass point C, that is the elastic limit, you enter a different region, something known as the plastic region. So if you stretch it too far, then it will lose its elasticity. It won't be able to snap back to its original shape. And so by applying a force that's too high or too much, then you could permanently deform the solid. If it doesn't return to its original shape, it's in the plastic region. So that's between point C and D. Now, if you apply too much force, then you could reach the breaking point, at which point the solid could snap into two pieces. It can fracture. And so that's the breaking point of the material. Now, the ultimate strength of a material tells you the maximum force that can be applied without breaking the material. Or basically the maximum force where it will take you to the breaking point. Beyond that, the material is going to snap. So what I want you to understand is that the breaking point represents the maximum elongation. So you could think of it as delta L max. And the ultimate strength represents a force. It is the maximum force at which an object can remain intact without breaking. Once you exceed that ultimate strength or that maximum force, it's going to break into two parts. Now let's say if we have a cylindrical solid, and we're going to apply a downward force. So we're going to compress the solid, and so it's going to shrink in height. So here's the area. This is the original length of the material, and this difference here is the change in length of the material. Now you need to be familiar with two terms, stress and strain. Stress is the ratio between force and area. So this is technically called compressive stress because we're compressing the material. If we're stretching it, it's known as tensile stress. Strain is the ratio between delta L and the original length. For tensile strain, when you're stretching it, it's delta L is positive, but for compressive strain, it's negative. But let's not worry about the negative sign. I just want to give you the general terms for now. So make sure you understand that stress and strain. Now, what do we get if we divide stress by strain? If we divide those two, we're going to get something known as the elastic modulus, also known as Young's modulus. So some textbooks might have Y instead of E. So it's the ratio between stress and strain. Now, stress is something that's applied to the solid by external forces. So if you apply a force over a small area, there's going to be a lot of stress applied to the material. However, if you apply the same force over a larger area, then the stress applied to the material is much less. So stress increases with increase in force. However, you can decrease stress by increasing the area upon which that force is applied. So if you wish to decrease the deformation of a material, you can decrease the stress applied to it by increasing the area. So let's say if you have a very thin metal, a very long and thin metal, it's going to be easy to stretch or compress it compared to a very thicker or a much more thicker metal. This is going to be hard to stretch or compress it because it requires a lot of stress, a lot of force to change its length because the area is so huge. So make sure you understand that. It's easier to stretch or compress a thin rod as opposed to a thick rod. So stress is force over area. Now strain, on the other hand, is a measure of the material's response to the stress applied. It tells you the fractional change in the length of the object. And as we said before, strain is the change in the length divided by the original length. So we could say that the elastic modulus, or Young's modulus, is F over A divided by, that represents this big fraction, delta L over L initial. Now perhaps you heard of the expression keep, change, flip. Perhaps you heard it in algebra. We're going to keep the first fraction, F over A, change division to multiplication, and then flip the second fraction. Now the elastic modulus tells you the strength of the material. For example, steel is very strong. It has an elastic modulus of 200 times 10 to the 9, and the units is newtons per square meter. Delta L and L0 are in meters, so they cancel. Force is in newtons, area is in square meters, so the elastic modulus is going to be newtons per square meter, which is basically equivalent to a Pascal. Pressure is force over area, and 1 Newton per square meter is equal to a Pascal. So you might see the elastic modulus represented in newtons per square meter or pascals. And they're equivalent to each other. So just keep that in mind. So this is the elastic modulus for steel. Now let's compare it to another material. Let's use wood as an example. Steel is a lot stronger than wood, and the elastic modulus for wood, let's say if it's parallel to the grain, it's about 10 times 10 to the 9 newtons per square meter. So based on this, steel is 20 times stronger than wood. So what you need to understand is that if you're looking at a material, and if the elastic modulus is high, it tells you that you have a very strong material. That means that you can apply a lot of force and the material is only going to change its length by a very small amount. Whereas something that is, let's say something that's weaker that has a lower elastic modulus, you can apply the same force and it can compress or stretch by a much greater distance. And so it's easier to fracture or break a substance that has a lower modulus. But steel, it's harder to break steel, and so it has a very high elastic modulus. So the higher the E value, the stronger the material is. So it's going to be a lot harder to fracture something or break it into two parts whenever that something has a very high E value. Now let's go back to the equation that we had at the beginning, or earlier in the video, where we said the elastic modulus is force over area multiplied by L0 divided by delta L. So let's solve for delta L. Let's multiply both sides of the equation by delta L times A. So on the right side, these will cancel. On the left side, we're going to have E times delta L times A, and that's equal to F times L0. Now let's divide both sides by EA. So delta L is 1 over E times F divided by A times L0. So we can see F and L0 are on top and EA are on the bottom of the equation. Now you might see this equation a lot in your textbook. It might be represented in this form. But I want to discuss the effects on delta L of certain variables. For example, we said that a substance with a very high E value or very high elastic modulus value doesn't change its length as much as a substance with a low E value. And because E is in the bottom, it's inversely related to delta L. So with a substance that has a very high elastic modulus, the length of that substance will not change if you keep the force in the area constant. So a substance with a very high E value or a very high Young's modulus value will have a smaller change in length when you apply a force to it or any sort of stress to it. So as we mentioned before, substances with a very high elastic modulus like steel will experience a smaller change in length. Substances with a very low elastic modulus like wood will experience a much greater change in length given the same amount of stress applied to it. Now the area is also in the bottom of the equation. So the area is inversely related to delta L. So if you increase the area of a substance, the change in length will decrease. And as we mentioned before, let's say if you have a very large object, it's going to be hard to stretch or compress it as compared to a very thin object. So a thin piece of metal is easy, it's much easier to stretch or compress a thin piece of metal. But a very large, thick piece of metal, it's harder to stretch or compress it. So if you decrease the area, you can easily increase the material's response to an applied stress. Now the next thing is the force. Notice that the force is on top of the equation. So force and delta L are directly related. If you increase the applied force, the change in length will increase proportionally, as long as you're in the elastic region, or rather within the proportional limit. In the graph that I drew before, that's between points A and B. Up to the proportional limit, it follows Hooke's law, F equals K times delta L. Now the last thing is L0. As the length of the rod increases, the change in length will increase as well. So it's a lot easier to stretch a longer rod than a shorter rod. So this rod will stretch more than a shorter rod. But the fractional change will be the same. Now, starting again with this equation, let's calculate the force. So what I'm going to do is multiply both sides by Young's modulus and the area. So on the right side, these will cancel. On the left, I'm going to have delta L times E times A, and that's equal to F times L0. So now all I need to do is divide both sides by L0. So the force is equal to, I'm going to write it a certain way. That is E times A divided by L0 multiplied by delta L. So as you can see, these three things is still on top, and L0 is on the bottom. Now the reason why I wrote it that way is to relate it to this equation. F is equal to K times delta L. So you can see that K, the proportionality constant, is based on E, A, and L0. So K, the proportionality constant of, let's say, anything that's elastic that can stretch, depends on the elastic modulus, which is based on the material's property. It depends on the area of the material and the length of it. So K depends on the dimensions of the material and also the properties of the material itself. Some materials are stronger, some are weaker. Some are longer, some are shorter, some are wider, and some are just thinner. So therefore, we can say that K is equal to elastic modulus times the area divided by L0. Now, what is the difference between something with a small K value compared to an object with a large K value? If an object has a large K value, that means that it's very stiff. It does not want to stretch or compress. So it's a very strong material. Something that has a very small K value changes its length very easily. Think of a rubber band. It's very easy to stretch or compress it. So it's like a loose spring. It's easy to change the length of that material. So if you want to make something that's stiff, that's very strong, you want to increase the K value. So you want to choose a material with a high elastic modulus, something like steel or iron, and you want to make it very thick. So you want to increase the cross-sectional area of the object. So you want something that's very wide as opposed to very thin. And the last thing you want to do is you want to decrease the length of the object. If you decrease the length, the K value will increase.